Hello and welcome to Vidush Academy. Today we'll be diving into stock analysis with a Monte Carlo simulation, and we will see how the prices can be a bit forecasted. As usual, none of this is any type of investment advice. So let's take a look and let's start with importing Yahoo Finance, NumPy and Matplotlib in our video. So the first segment of the video would be to take a look at the stock that we will be simulating, and it's Coca-Cola, and the data would be downloaded with Yahoo Finance download using the stock, and then the start would be from 2020 0101, and I'll put an end in the end of this year, so it will work a bit more if you are copying the whole code. And let's try like this. See the data. It is here. We have close, high, low, open and volume. We would be concentrating on the close ticker. So let's say we need the data close, and it would be like this. Let's use see the head again, or the tail. So we started with 40 something, we ended with 70 something, and this is not counting dividends. Okay, sounds great. And now let's take a look at the price ratio. How do we calculate it? It would be data close divided by data close, shift 1. As easy as this one, pretty much saying what's the difference between each day in the closing data. And we will be calculating returns, not return, because return is a really safe word in Python. Let's not use it for variable naming, and we'll be using np.log data close divided by data close, shift 1, and we'll be dropping NA just in case. Now let's think, why do we use np.log and not the standard way? That's an interesting question. What do we earn this way and what not? Let's pretty much make some kind of example here. Here I'll call this one y using logs for return, and I'll translate it as a markdown, and it would be even like a header, but as a big header, something like this. Okay, so now let's make a list of prices, and we start with 100, 110, 99, 108, 95. As simple as this. We have 5 prices, not bad. And after these prices, you will have like 2 methods called simple return, which would be pretty much, I'm just hard coding 100 minus 110 minus 100 divided by 100, just to see the gain. And of course it's this one minus this one divided by 100, so it is in percentage. And then we'll have log return, which would be np.log of 110 divided by 100. Great. How much is the log return? Something like 0.953 something. Yeah, I'll just write it like this, 9.53%. log gain. Yeah, makes sense. And the simple return is 0.1, which is 10%. 10% gain. Yes, what do we earn out of this? And why is the one better than the other? The answer is that actually none of these two is better than the other. Pretty much simple return is used to calculate actual profits and loss, and it is quite useful and easier to explain to anyone because this is how the real world functions. Then why am I using here log returns, which is somehow not exactly correct, but it can be correct if I use like something like this. If I use log return MP exponent log return, yeah, it is correct, and I can even remove the one, so it's perfect. Yeah. And yeah, let's consider this 0.1, 10% exactly. This is not a mistake of Python. So back to the point, why do we use log return? Because returns over multiple periods sums nicely, and we have this kind of symmetry that I'm actually interested in for the whole idea. You see, 10% gain is 110, and then a 10% loss would be back into 99. But in our case, if we were using like log returns, this would be cancelled. And for our model, it is better to be cancelled out. Although in the real world, if we go with 10% up and 10% down, it's not cancelled. We are at 99 if we start from 100. So, as I said, the log returns is better in a statistical modeling. I'll try to explain this later better in the Jupyter notebook itself. So let's continue. Let's plot the returns with a cumulative sum and see what's going to happen. Yes, it happened quite nicely. And just to see, we're talking about these ones here. These are the prices of Coca-Cola, and they are actually not bad. You can take a look how there are smooth periods after 2021, and talking about here and how they differ from the volatile 2020, and it's really well visible in the simulation here. Yeah, what can we do? We can also try to plot the data close itself. It should be like almost the same, not exactly. You see, what should you be seeing as a difference? Well, this one here seems to be a bit smaller, I would say, than this one here. And of course, you see here real numbers. But in general, the figure looks the same with this exception here. That it really looks bigger up to the down. And probably also here, this one looks a bit higher, but this is a good one. Okay. I'll simply exit like this one, and I'll continue with our analysis. Okay, so now let's calculate annualized return, annualized volatility, and see what we can do with this and how can we use them in our Monte Carlo simulation. So in general, for trading days, it is considered that the year has 252 trading days, so this is what we would be interested in, and the annual returns for our calculation should be something like returns.mean times trading days. Fair enough. So let's take a look at the volatility. We would have here returns.std, which is standard deviation times squared trading days. Okay, and let's see, annual return, print, and then print standard annual volatility. Okay, so annual return is like 8%, which is rather good, and the volatility is about 20%, which is also not that bad, not at all. And now, time to go to Monte Carlo simulation. I'll use like this. And I'll be using Markdown. And I'll be using Markdown like this. Okay, so the Monte Carlo simulation, number of simulations will be 10,000. I really like the underscore here. This way it is easier to present what's going on and it's visible for everyone. Then we're talking about 10,000. And what else? Starting price. Starting price would be data close -1. Ta-da. Just to show you like what is here in data close. This one, you'll see that it just took the last day available. So today is actually the 4th of May, but it took the 2nd of May because this was the last working day of the stock exchange for Coca-Cola, for which Yahoo has data. And for example, if we do -2 here, it would give us the last 2 days, the last 2, the last 3, the last 5. This is called slicing and dicing in Python, and it's actually useful. But we only need the one price, the value, so we are gonna use values 0 and then item, and I will put a comment here, last available price. So just to see whether we got the correct one, starting price, okay, 71.65, yes, this is the last one that we had. Okay, let's continue daily returns and price bets. Daily returns, we'll use MP random, normal, so annual return divided by trading days. Then we have annual volatility divided by MP SQRT trading days. And we have a comma here. And we'll have trading days and number of simulations. I'm looking for this one. And of course, it doesn't work well every day. Let's take a look. Annual return divided by trading days for sure. Annual volatility divided by MP SQRT trading days. SQRT trading days, shift and enter. Then trading days, we'll remove this, simulations, and everything should be okay. So the daily returns looks like this, not that bad, could be useful, and it's actually correct one. This is data. Now the interesting part is to do price bets, and they will be using starting price. So for each of the number of the 10,000 simulation that we are having, our starting price would be this one, the real one. So starting price time NP cumulative product 1 plus daily returns x is 0. Okay, let's see what we get in price paths. We have a lot of stuff. Count. Okay, I mean I'm just using plan. 252. Of course, we got them for each day. That's good. And our days are here, trading days. What can we actually do with this one? Well, we can plot it, and let's try our best. PLT plot, price, paths, and should we be plotting everything? That's a good one. I'll just plot the last 5, and then let's see. Okay, I am adding a line starting from the starting price. The color would be thinking about, okay, black is a good color, yeah, or white. Okay, white, and then line style, something like this. Let's see. So these are the last 5 simulations, and we see the white color for the starting point. Okay, I'll return to black now. Obviously not a good decision. Yes, now it looks better. And these are like the prices, and these are the 252 days. We see that in the last 5 simulations we have one that really went up to the top after going like this, that and that. You can simply even go into the last 2 simulations, which are rather unfair for this stock. But in general, with fast computers, I mean faster than mine, you can probably use even 1000. I'll use it like this. And this is how it looks with 1000 simulations. We see that there are some outliers like this one going over 140. We can even make all the 10,000 simulations, although it's a bit unfair and probably not so useful, because it would take 10 times more than the 1000, and the 1000 was already taking a lot. Okay, we see that a lot of the simulations go above today's price, and quite a number goes also below, and this is Monte Carlo. So let's try to make something better out of this. The question is how. Let's try to put this data into some kind of buckets so it is more visible for us. So we would have buckets count, and the buckets count will be here. It's a variable 30, and then we would have edges. The edges are actually bucket count plus 1, and we need price bins, so we use line space NP mean price paths, and here we have NP dot max, and here we are using edges. Quite fair. Numpy has no attribute line space. Of course, I always mistake this one. It's something that everyone does. So price bins, we have them. This is where the cutoff is. We see like we have 30. If we have like 5, the cutoff would be somewhere else. And of course, as noticed, 5 bins means 6 edges, so we have them. Now we should plot it. Let's have it here, PLT figure, and the fixed size is the standard 12/6. It's pretty much everywhere. Then some histogram price bets. So from -1 to here means this one means everything. And then the bins would be the price bins. Each color would be black or yellow. Let's try with yellow. And an alpha of 0.7. Fair enough. Okay, we have it. What it doesn't like, rectangle set got an unexpected keyword argument each color. Okay, this shouldn't be fixing it, but sometimes it does. Okay, what about blue? Okay, what about black? Oh yeah, I got the point. It should be like this. So yellow, and it looks good. We'll be using something like 30 bins. Yeah, not bad. And this is how our 30 bins look like. What would actually make more sense is if we write explicitly the current price from which everything started. We called PLT XV line from starting price, color red, and what else? Line style should be like that, and of course a label called current price. Let's take a look. And there should be POT legend and POT show. Legend, POT show. Yep, looks okay. What else do we need? We need a title. And it will be something like stock. Monte Carlo final price distribution. And we'll use here bucket counts. Buckets. Yeah, makes sense. 30 buckets. This is how it looks like. And let's put something on the X and on the Y axis here and here, because we all know the XYCD, XKCD joke that if you don't label your plots, things are gonna be bad for you. So here we say price in 252 days. I'll just write it like this, and here I'll put the days, and Y label, it would be a bit different. Number of simulations. Number of simulations, price in 252 trading days, because 252 is like a year. Okay, fair enough, I would say. And now let's think. What do we get from all this? I mean, we simulated 10,000 runs of Monte Carlo, great, with some kind of fancy formulas that they are not so complicated, but they're kind of okay, I would say. Even they only take like what, 3 things: trading days, annual return, and annual volatility, with some price pads saying like we can go to the random up, we can go down, we can do a lot of stuff. But what is it telling us? I mean, should we buy or not? In general, just a reminder, none of this is any type of advice, especially financial advice. I'm just showing stuff. But in general, if we want to calculate some risk metrics, here is what we should do. Pretty much the most important one is the loss probability, which is pretty much simple as it can get. We calculate the times and the simulations where final price is less than starting price. So let's do it. I mean, from here, I'll see that it's over 50%. We will be on the good side, and here we will be a bit not exactly on the good side, but happens. So it would be more than 50% for sure. So let's see how to calculate it. We have price pads. Bigger than starting price. And then we care about the mean of this, pretty much saying the starting paths -1. This is the last one. Pretty much the price is here in the last 252nd day. And then we get the mean, and then because it's a probability, let's do it with 100 and see what this is. So yeah, in this case, we should be with a loss in around 40% of the time, which is a good question. We'll probably lose money 40% of the time, but if we want to be like, I don't know, bad guys, we can do something like this. Change it from 2022, run again our timing, and see that it's actually 31%. What will happen if we do it from 2024 or 2023? Okay, when the stock wasn't so volatile. I'm just thinking. Yeah, let's see. No, here the loss probability is only 16%. So the thing is that you can actually massage the data quite a lot, depending on what you want to show to whom and what is your target. So loss probability in this case is whatever I said last, which is 38.94. Yeah, not bad. The second thing that we care about is the worst 5% of outcomes. So let's go to var5, and it's calculated this way: MP percentile is price pads -1. These are the last dates. The last prices, the prices at the last date, and we only care about the worst 5% of the outcomes, and these are somewhere here, 53, which means that if now we started with what was the current price. Let me see. Data close tail. The ending price for was 71, and it means that the worst 5% in our calculations were 53. Well, it means if it ever hits 53, run. In general, And what else? Let's see some kind of a central tendency, calculating the median and the first and the third quartile. I'll call them Q1, Q2, median, Q3. Okay, Q2 underscore median, Q1 underscore first, Q3 underscore third. Yeah, makes sense. So MP percentile, and this would be price bet, taking the last day of the price bet, and then only taking care about the 25th, 75th, and 50th, somewhere between them. And now let's take a look at what can we do. So Q1, okay, Q1 first means 65, so 25% of our simulation are less than $65, which is something. Q2 median 76, and in more than 50% we are making more than 76, which is good. And Q3 should be something really high. Q3 is 87.39, and then something else. Okay, so before making the summary of everything, I will improve a bit the outlook of this one, and let's try it once more. So let's summarize everything that we have done. For the summary, I'll use another stock. I'll use Pepsi, and I'll restart the kernel. So pretty much we downloaded the stock from 2020 up to the current date, whatever it is, up to December 31st. We took the data close. Just let me see whether data close tail would produce actually something. Yeah, produced Pepsi, and it's in USD, in dollars. Price ratio, we have calculated it with logs, and with logs it is better for our purposes, because this way a 10% gain and 10% loss would cancel out, as in this example here. Okay, then simple returns, they look okay, and they can be returned by exponential. Yes, then we plot, and this is how the price of Pepsi looks with the log returns. Let's take a look how it will look like on the second one. Well, not that bad as well. Okay, you see them both plotted, and that's the funny part. This one is just a blue line here because it was around the zero, and the other one is here on this one. Yeah. Then we take a look at the trading days. The annual return of Pepsi in this case is 258 since 2020, not calculating, of course, dividends, which is something. Annualized volatility of 22%. Then the Monte Carlo simulation, I'm just curious what would be showing up here. Well, we have a lot of things going up and a lot of things going down. We put them in buckets. This one on the left look actually pretty stable to me. I'm curious. Okay, price bin, I'm going to remove how it looks. I have put some data here about calculating the risk matrix, and let's see the loss probability. Probability of losing money 49.9. Wow, it's not bad, definitely not bad. Not very good as well. Worst 5% of the case. We have 30% drop. Then for Q1 we have minus 14%. For median, as I said, this 49.9 is about 0%. And for Q3 we have 70% increase, which is quite okay, I would say. The good thing is that with a tool like this you can analyze anything. Let's use another one. I'm thinking about using Tesla. And Tesla is an interesting one. Let's see. Let's run it quickly. This is the data close. And let's take a look at the other one. Yeah. From 2020 up to now, Tesla is doing great. And this is obvious. Annual return of 43. And the Monte Carlo simulation with this 68 volatility would be crazy. Yeah, it is. There is one scenario here even where Tesla goes with 2500, 1 out of 10,000, but it is a scenario. Then the buckets, well, the buckets are almost all positive, and the risk metrics pretty much after 252 days, and our simulations are, it shows that 25%, the top 25% of the simulations are over 562, which is 96% increase. The worst 5% are with 60% drop. Probability of losing money, this is an interesting one, 40, close to 40. Yeah, and as I said, this one is just simulation. Nothing knows what's happening. And so far so good. I hope you enjoyed the video. I hope it brought some kind of value into your ideas, what you can do with Python. And that's pretty much all from me. Enjoy the rest of your day or night. Take care of yourself. Goodbye.